Yeah, so it's like, I don't know what to do in my reflection because he has what it said. Yeah, he already talked about it, so.
So just to emphasize, it's recording. Thank you. Just to emphasize maybe the obvious, if we wanted to do the analysis that came up with the intercept and slope that we had for the two variables that we're working with, we would just do regression, and we're doing linear regression. And then our dependent variable is going to be their salary. The independent variable is going to be their publications. We'll talk some about these different methods, but the default is exactly what we're interested here. We're going to talk more about some of these statistics and how they can be useful as we diagnose our analysis. We'll talk about some of these plots and what we might do with those, and we'll talk about some of these other options and how those can be useful. But for the most part, we can just do that, and we get and we'll talk about, well, what is this ANOVA table, and we'll cover that here in a little bit. But these are our coefficients, and so these are the values that would be our constant is also intercept, and so this would be our intercept, and then this would be the slope. And that should match up with what you have, assuming I didn't change the data in the data file. And then the standard error, we'll talk a little bit about the standard error here, but we'll talk a little bit about, we won't calculate the standard error, but we'll talk about how we can use the standard error. And then the beta, we'll talk about that when we talk about multiple regression. And then the t-test, we'll talk about that as we move forward as well. So just wanted to, for those of you, if it wasn't completely clear, where does the intercept and the slope come from? They came from me running this analysis and just putting them on that slide that we had. So there was no calculations that I did by hand, nor would I expect you. So that leaves us. Here. We'll come back and review this slide when we start class next week, because it really is sort of foundational to our understanding, particularly what is sums of squares total, what is sums of squares regression, and what is sums of squares residual. But if there are no questions about this slide now, questions? No? No? We can continue. We can continue with how do we know? We could just randomly generate two variables, just using a random number generator, and how and we could tell SPSS to generate a regression equation, right? That will have some intercept and some slope, and it would do that. But the question, and if they're randomly generated variables, randomly generated data, it's all just noise, right? There's no signal there to be gleaned. It's just randomness, and so it's just noise. And how do we determine whether our regression is just noise? Essentially, I know that you're not going to be working with just two randomly selected variables, but mathematically, there might not be much of a relationship between the two variables, and from mathematically, it appears like it would be noise, or it is noise, no different than if we just used randomly generated data. So the thing that we want to think about is, how do we understand if our regression of y on x is meaningful or significant? And as you would suggest, or as you probably are thinking, this significance implies some kind of hypothesis test where we have some p-values, and in this case, an f-value that we will look at. And so we're going to do a significance test to understand whether our regression of y on x is just noise, or if there's some signal in those variables. And in other words, does x explain more variance in y than we'd expect to get by chance? Because if we just generated random data, again, we'd be able to get some equation, but it's all noise. It's just all chance. There's no signal to be found there. And so what we need to know with our data that we're working with is there some signal in that relationship between x and y? In other words, is sums of squares regression? By the way, is that the good sums of squares or bad sums of squares?
Good.
Yeah. Is good sums of squares greater than we'd expect to get by chance? Because just by chance, it's not going to be 0. It will be some number greater than 0, but at what level does greater than 0 become, when does that become meaningful? And that's where the hypothesis test will allow us to test how likely is it that it's just noise, or is there some signal there? And so for each of the sums of squares that we talked about earlier, there's an associated degrees of freedom. And so the associated degrees of freedom for sums of squares regression is equal to the number of independent variables in our analysis. The associated degrees of freedom for sums of squares residual is n minus k minus 1, where n is the number of rows of data you have, or the number of observations of data you have, or the number of cases that you're working with. And sums of squares total, the degrees of freedom is equal to n minus 1. And I want to just pause 1 minute to talk about, well, when you say degrees of freedom, what does that mean? And give me an example of that. And I can give you a pretty concrete example that would get more complex as we look at other scenarios. But this is a pretty straightforward scenario, and it's the looking at sums of squares total, where degrees of freedom is equal to n minus 1. And by degrees of freedom, what we mean is, in this case, n minus 1 scores are free to vary, but the nth can't vary. It has to take on a particular value. And so n minus 1 can vary, take on any value they want, but when we get to the nth score, it isn't free to vary. It has to have a particular value in order to just satisfy. It doesn't have to have it. Just that's the way the math works. And so if we think about this data, and this is where we came up with, this is our sums of squares total, right? And I said sums of squares total has n minus 1 degrees of freedom. And if you think about that, this column has to sum to 0. It sums to 0. If I could round out to 100,000 decimal places, this would sum to 0 at 100,000. But that number, even though it maybe doesn't look like 0, it's close enough to 0 for anything that we care about. So this column has to sum to 0. If we take, in our case, salary minus the mean, or in any other set of data, take the score minus the mean for the set of data, and do that for all data, and sum this up, it has to sum to 0. So only n minus 1 are free to vary. The nth, whatever the nth one is, it doesn't matter, just pick any one. Whatever the nth one is has to be a value that gets this to 0. And so only n minus 1 are free to vary. The nth has to be whatever value gets this to 0. And so we say the degrees of freedom are n minus 1. And so that's that again, speaking of intuition, that's sort of the intuition behind when we talk about degrees of freedom. That's the intuition behind it, that in this example, n minus 1 of those can take on any value that they want, but when you get to the nth one, the last one, it's constrained. It can't take on any other value than a value that gets this to 0. So it is not free to vary. It has to be a value that gets that to 0. And so that's why the degrees of freedom for standard deviation for the sample is n minus 1. When we're dealing with population data, we don't have the same challenge, and so if we're dealing with population, we use n instead of n minus 1 for the calculation of standard deviation. So that is just some maybe cursory understanding of what is degrees of freedom, but it really is that idea of scores being able to vary. So we have these associated degrees of freedom that we're able to then, and what we do is we divide the sums of squares by its degrees of freedom, gets us a mean square. And then the ratio of the mean square regression to the mean square residual follows an F distribution with degrees of freedom equal to sums of squares regression and sums of squares. The degrees of freedom equal to those of sums of squares regression and sums of squares freedom. So we calculate this ANOVA table. In our case, fortunately, SPSS is doing it for us. But what it's doing is it says sums of squares regression is 201.953. Degrees of freedom is equal to the number of independent variables, which in our case is 1. 201.953 divided by 1, of course, is 201.953. Sums of squared residual is equal to n minus k minus 1. So that's 8, right? Our n was 10. 10 minus 2. And so we take our sums of squares residual and divide it by 8, and we get 13.991. And then sums of squares just as a point of clarification or of just an observation, the degrees of freedom for total, sum of squares total is n minus 1, and that's 9. And so we can divide the sums of squares, the mean sums of squares regression by sums of squares residual. The good sums of squares, the good mean sums of squares divided by the error or the bad sums of squares follows an F distribution. So 201.953, if you put that in your calculator, divided by 13.991 is going to be 14.434. And then SPSS is nice enough to give us this significance level here. And so in our case, we would reject the null hypothesis that the relationship between x and y is 0. And we would reject that for the in favor of the alternative hypothesis that it's not 0, that it varies in a meaningful way from 0. So far, so good? How many people have their book with them? How many people have the free online downloadable copy of the book? So let's or you can do a Google search and get an F table. Let's. This is like fun with statistics, finding an F table and confirming these values, and And it's just, I just think it's one of those things where if you sort of have some understanding of, well, where does this come from, this 0.05? Well, of course it comes from the black box, but we could also use a table in the back of a book to get the same thing. Or you could find a F table. If you just do a Google search for an F table, it's going to look slightly different than ours, in all likelihood, but it's going to get us the same result. So where is the F table in our appendix?
944.
944 is where the F table starts. So this F table, this F table is a little strange in that and so we have across the different columns is the numerator degree of freedoms, and then the rows represent the denominator degree of freedoms. And so our numerator degree of freedoms, right, because we calculated this ratio, our numerator degree of freedom is 1, right? And so we're going to be working with this first column right here, right? So we can narrow it down to that column. And then our denominator degree of freedom is 8, which puts us down at the bottom of the page, at least on the table that I have, bottom of 944, and then the top of 945. And so what we would do is, so these are, you see the percent signs that they have at the top of the table. These are actually in percents, which is sort of the weird thing about it. And so what we want is the 5%, because that would be sort of the minimum. We always 0.05 is sort of the cutoff that we use, and so we would use the 5% in our table, and we could go then. So I'm at the top of page 945. What's the F value at 5%? 5.32. And so there's two F values that we work with. One is called the calculated F value, and one's called the critical F value, right? Does that vernacular ring any bells? We have a calculated F and a critical F. This one that we just looked up is the critical F. And so our critical F is 5.32. Our calculated F is 14.434. Is our calculated F greater than our critical F? Yeah, and so if it is, then we can reject the null hypothesis. And the null hypothesis is that there's no meaningful relationship between the variables. And so we reject the null hypothesis in favor of the alternative that there is a relationship between the two variables. And so we that would sort of be the easy way. That would be the easy way to do this calculation. To get this same, you wouldn't get this value, but you'd be able to say P is less than, in our case, clearly less than 0.05. And then you could also look, and you could go 2.5, right? It's 7.57, and we're less than that as well, right? And 0.01, or what they call 1%, is 11.26. We're less than that as well, right? And so we could say confidently that P is less than 0.01. Yep. And then we could keep working our way down the table. 0.005 is 14.69. Our table says, right? Do you get the same thing? 14.69, which is awfully close to 14.434. And so they're just rounding this if we actually looked in SPSS, this number is rounded to this value. If you double clicked on this in the table, you would see that it just rounds to 0.05. So what we confirmed is that SPSS did, using the F table in the book, that this value does seem to be correct, right? And there would really be no reason to doubt it. If the software can't do that for us, it's probably not able to do much of anything. But it is useful to know that this isn't a black box. It doesn't have this table stored somewhere in the black box either, that it's indexing. There's another formula that it uses that it makes it more efficient to come up with what this is. But we could write our own software if we wanted to, and we could put this table in there, and we could index this table with those degrees of freedom, and we could easily produce something that looked very much like this. So I just think there's some value in understanding, at least for this F test, where this comes from. And we'll do a T test in just a minute, okay? So far, so good? If I gave you an F table, and if I gave you, this is referred to as an ANOVA table. If I gave you an ANOVA table and left this part off, left off this part, the significance level, would you be able to use the F table and come up with what the significance is? We'll try that. We'll try that at the start class next week. All right. So bring your book or bring your digital copy of the book. So that answers that question. How do we know if our regression of y on x is meaningful? Well, we do an F test, and if we reject the null hypothesis, then we have some confidence that the relationship is more than we expect just by chance. And so another question is, well, how strong is the relationship between our independent variable and the dependent variable? And we assess that with an effect size measure. The sort of proper name for it is coefficient of multiple determination, which I don't ever hear anybody refer to it by that. It's always just R squared. And R squared represents the amount of variation in Y. Maybe Amy Johnson would be the only person that would, her statistical training is very formal in that way, and she'd probably be somebody that it wouldn't surprise me if she would use that. And so good for her. That's just, I think most other people would just say R squared. I certainly would. And so R squared represents the amount of variation in Y that is explained by our analysis, by our equation, i.e. what is the effect size. And so R squared is a pretty simple calculation. It's just sums of squares regression divided by sums of squares total. So it's good sums of squares divided by total sums of squares will give you your R squared. And it can't be greater than, right, because sums of squares total is total sums of squares, and there's no way that it can be greater than that value. So the max is going to be 1 if we're perfectly explaining the dependent variable with the independent variable, and the min will be 0. Although I've never seen it be exactly 0, it can approach 0. And so in our case, if we wanted to calculate sums of squares regression, we could just flip back here, and we could divide 201.953. Let's do that once just to make sure. Somebody have their phone. 201.953. Divide that by 313.885. And what does that come to? Hopefully it comes to something close to 0.801. Or I'm sorry, 0.643. Point what? 0.64. And so that would be R squared. Of course, if we wanted R, how would we get R? What would be one way to get r? If we have r square, take the square root of it, right? And so take the square root of 0.643, and you'll get 0.801. There's another way to get r that I think I talk about here in a couple more slides. And then we're going to talk about the adjusted r square on the next slide. So r square always goes up when additional independent variables are added to the equation. If you sort of think about that math that we looked at where we are calculating the sums of squared residual, that's always going to be a positive number. And that will always mean that as that goes up, sums of squares regression goes down, and consequently, as you add independent variables to your analysis, necessarily so, mathematically, because it's just a fact, r squared will always go up. So just add an infinite number of independent variables to your analysis, and you'll explain, in theory, 100% of the variation in your dependent variable. And so there's an adjustment that we do, and that's the adjusted r square, that considers and the number of independent variables, and there's an adjustment that gets made. And essentially, if you have a bunch of variables in your analysis that are not contributing to the explanation of the outcome variable, you will pay the price with a lower adjusted r squared. If all of your variables are significantly related to, in a meaningful way, related to the outcome variable, the adjusted r squared will decrease when compared to the r squared, but it won't decrease as much as if you have a bunch of variables in your analysis that are not making a contribution. And so it's a useful calculation. And I don't think I give you the formula for it. The formula is actually pretty straightforward. Your textbook gives you the formula for sure. And there's plenty of other places where you'd be able to get the formula for adjusted r square. In our case, r square is 0.643. Adjusted r square is 0.599. I would encourage you to always just report both of them. It's useful. It's just a useful. It's a useful measure to have for the reader.
Are these like, I know you can make charts, but is this a chart that you also got by going to regression, linear? Like
Yeah, this is a part of the output. Yeah, this is just the default output that everything here is just put in your independent variable, say, okay, and you're going to get all of it.
I was just making sure it was all still.
Yeah, everything that we looked at so far. So that's adjusted r square. So we'll get back to, I mean, there's a reason why the r is there too. Of course, we can get the r by just taking the square root of r squared, but there'd be another way that we could get the, if we wanted to, we could just calculate r and then square it to get r squared. The calculation would be more complicated than just dividing the two sums of squares, and we'll get to that here shortly, and we'll come back to that table. So that leaves us here. So in our case, we did the F test, and the F test is really testing think of the F test as, is your r square significantly greater than 0? That's what's being tested there. So is the r squared that's reported on the next page, is that significantly greater than 0? That's what this is testing. And so in our case, because we only have one independent variable, and if we know that the overall R square is significant, we know that necessarily so that that one independent variable has to be significant as well, because how else would this be significant if that one independent variable wasn't allowing us to make that prediction. But in most cases, as I mentioned, we're going to have multiple independent variables. And so we'll be able to sort of at first glance look at, is the R square that we're explaining, is the variation that we're explaining in the dependent variable greater than we'd expect to get by chance? And if it's not, then just stop right there, right? Because your analysis does not help to explain the dependent variable in a way that's significant. And so just, you're done, and you can report that if you want to, or you can continue to maybe run other tests that you need to run. And so that's sort of a two-step process. One, we look at overall is, are we explaining variation in the dependent variable in a way that's significant? If you answer yes to that question, then we go on and we look at the slope for our independent variable. Or in most cases, we're going to have slopes for multiple independent variables because we're going to have more than just one independent variable. So getting back to that test, we would ask, especially in the case where we're doing multiple regression, is the value of the B greater than we expect to get by chance? That is, does it differ significantly from 0? And B is tested with the t-test with degrees of freedom equal to n minus k minus 1. And the t value is equal to B divided by the standard error of B. Sort of similar to what you did with skewness divided by its standard error. Does anybody have what's standard error anyway? When we think of standard error, what is that metric trying to tell us? Similar to standard deviation. Anybody got somebody take a?
Is it just how much each data point is off the line?
In this case, it would be an indicator of that. Yes, and it's the standard error, be it the standard error of kurtosis or the standard error of the mean or the standard error of B, is a measure of if we were to replicate this study with the same population, how much variability would we expect to see in the calculation of B? And so as standard error increases, we would expect to see greater variation in our B. Does anybody remember the formula for the standard error of the mean? It's a useful standard error of the mean. We can use the standard error and the mean to do some similar things to what you did with kurtosis and skewness for this week. We haven't talked about the formula yet, but does anybody remember from previous class? It includes standard deviation, but do you remember the formula? Chris, it's really easy. Standard deviation divided by square root of n. So that's the formula for the standard error of the mean, and again, it's a estimate of if we were to replicate this study, how much variation, given the n that we have, how much variation would we expect there to be in the mean? And of course, as n goes up, standard error goes down as a function of the square root. And so sample size of 10, all things being equal, you're going to have a much larger standard error than a sample size of 1,000. And it seems it seems reasonable to me that if you have n equals 10, well, that's a small sample, and you could go out and ask 10 people those same questions, 10 different people, and you might get wildly different answers. But if n equals 1,000, that's it would take a lot of different people giving you different answers to move that number in a meaningful way. That measure of central tendency. It's not going to be exactly the same, but it's going to be all things being equal, certainly more stable than if your sample size is equal to 10, because if you replicate that, again, your mean will fluctuate quite substantially. And so, long story short, hardly possible at this point, but we can do t, which is b divided by the standard error of b, and if we go back to our is that the next slide I had? Yeah, sorry. If we look at the output, this was the output that I had, that I showed you earlier in SPSS. If we look at our B, and there's our standard error, and 1.314 divided by 0.346 is going to be equal to 3.799. And then we get a t-table with degrees of freedom equal to n minus k minus 1. N minus k minus 1, so in our case equal to 8. And we do that hypothesis test. In this case, this p-value is exactly the same as the p-value that we got with the f-test, because we only have one independent variable. And it just happens to be that that's the way that it will always work out. And what's the square of 3.799? So we've got a calculator handy. What is it, Chris?
201.953.
The square of 3.799?
Oh, sorry. I didn't
14.43.
What is it?
14.43.
And so that 14 is the same 14 as we get right here. So there's a relationship with degrees of freedom equal to, when the numerator degrees of freedom is equal to 1 for an f-test, it's always going to be equal to, take the square root of this, and then you're going to get a t-value, or square the t, and you'll get an f-value. And so, but degrees of freedom for the numerator for the f has to be equal to 1, or that math won't hold. And so here we have our test for our independent variables. Somebody, how do we interpret B? What's the interpretation of B? Explain to your mother what 1.314 is. How do we interpret B?
For every increase in publication, you have an increase in wage of $1,314.
Good. Mom would get that, right? She'd say, "Oh yeah, I got that." Yeah, and that's the interpretation that we'll always have for B. For every one level increase or decrease, there would be V amount of change in the predicted value of Y. And just think about the equation for a straight line, right? Y is equal to the intercept plus B times X, right? And X in our case is number of publications. And so every time we increment up or down publications, we'd expect Y to increment up or down $1,314. So that understanding, you need to, as you do your analyses, as we work with some additional analyses in class, we'll think about that, and it'll be useful for us to to keep that interpretation in mind. In some cases, it gets really funky, especially if you have what I talked about multicollinarity earlier in the class. Anybody remember what multicollinarity is?
Multiple IVs being too correlated to each other.
Yeah, and so if we have independent variables that are strongly correlated, your B's become really strange values that the interpretation is very problematic. Additionally, in some cases, the B's aren't particularly the interpretation of the B's become a problem because 0 isn't a possibility for some of the values that we work with. So age, for example, if you so we'll see some examples of that. But even with those sort of unique, sort of strange cases, it's still useful to understand what the B is. And then we have this other thing here that's the standardized coefficient, which is beta. And do I talk about beta here, or do I save that for? I save that for next week. This is the standard error of the estimate, which, if we go back, that's this value here. And so, just so we understand that particular piece of information has some value, it's the standard error, or it's the measure of the spread of y-scores around the regression line. That is, it's the standard deviation of the residuals with degrees of freedom equal to n-2 instead of our typical n-1. And I don't tend to make this comparison, but some disciplines do this more than I was trained to do or what I do. But some disciplines will compare the standard error of the estimate with the standard deviation of y. And looking at those can help you understand how well your equation predicts y, the degree to which it is less, that is, the standard error of the estimate is less than the standard deviation. We can think that we have a useful set of predictors for our data. The reason why I don't use it, it just doesn't, there's really no metric or sort of scale to place it on. And so in our case, the standard deviation of y was 5.91, and the standard error of the estimate was 3.71. Yes, the standard error dropped. Does it seem like it dropped a lot? Yeah, that seems like a pretty big drop to me. But if I don't have a lot of experience, it didn't drop that much. So intuitively, it doesn't do much for me. But there are some disciplines that this is a part of what gets reported. I don't see that done, at least in the literature that I read in communication. Political science would be more likely to give you the standard error of the estimate than I think you would see, at least in communication and public psychology. So is that it? That's it. Questions? It's 54 out, by the way. Questions, Chris?
So I have a question about beta weights and the way we often interpret them. So what happens when I transform my variable into, let's say, a logarithmic transformation, and now I'm looking at a beta weight that...
B or beta?
Sorry, beta. I'm looking at my beta and trying to make a meaningful interpretation, but that becomes extremely difficult when I'm looking at a variable that I've done a logarithmic transformation on, right? I can't, like, it's one logarithmic version of the variable up above.
I think if you're looking at the B gets really complicated, right? Because B, B is it's no longer and it depends on did you transform the independent variable? So let's say we did a transformation of the independent variable, and we took the log of it, and so the interpretation of B would be as that independent, for every 1 unit increase or decrease in that independent variable, it moves the dependent variable. You'd have to take the log of b to get it back to its original into its original its original form. In the case of looking at a bunch of variables where it's no longer age, but it's the log of age, which we don't think about, or it's no longer your 1 to 9 scale, it's the inverse of your 1 to 9 scale. That would be where I probably would use just the beta weights, because those have been standardized, and there's a standard interpretation that we can apply to those that would apply whether we were using the transform value or not. But you're right, if you are transforming data, the interpretation of B takes a lot of work. Readers of your research probably aren't interested in you trying to make that interpretation for them. And so the best way to get around that would be to use the standardized beta. And that's the piece that we'll talk about. We'll talk about this a little bit next week. If we just look at these coefficients. This has that's on a standardized scale. For the most part, between -1 and 1, although if you have a lot of multicollinearity with your data, it can go from -infinity to +infinity. But if your data is not problematic in terms of multicollinearity, the coefficient, the standardized coefficient would be the thing that I would try to interpret in that case. And but I think you would be able to, if you really had to, make the interpretation between B, some transformed independent variable, but to try to write that up in a way that would be consumable, I just don't know that I don't think it would be worth the heartache that you'd have to put into that. So the other thing you could do is, instead of using the transform variable, so you could transform your data and then standardize all of your data, and then your B would be equal to your beta. And so that would be another way to report it. And then there would be an interpretation that would apply, that there'd be some intuition that you could draw on, or some logic that you could draw on that would help you make that interpretation. Good questions. Other questions, William?
I may have just missed it or be confused. If you're looking at the B and you have a dichotomous IV, how does that interpret? Because obviously it's not.
It just would be the difference between a 1 or a 0, right? So
it's just the difference between groups. Like obviously you can't go up with like 2 groups. So
right. So so let's say we had males and females, and males were coded 0, females were coded 1, and we had just a 1 variable analysis like we had. The intercept would be the predicted value for the male.
Okay.
And then female, because they're coded 1, would be B times 1, or B plus the intercept.
Okay.
And then that's the extent of if it's just a dichotomy,
Okay.
which
That's what I thought. I just
yeah.
wanted to make sure.
Good question. Pavitra?
My standardized coefficient beta value and my R value is the same. In this instance, so is there how to do
Is it the same here too? So we have is it?
0.802?
Yeah, so I guess that's an observation that, so R is the same as the beta. Yeah, I guess that wasn't, it will only be the case in the case of bivariate regression. When we add in another variable, that will not be the case. But in this sort of unique situation, beta is actually the same as the correlation between x and y. Is it? Is that what I'm saying? We have a minute. So if we correlate, yeah. So the correlation between x and y is 0.802, which is the same as the r, which is the same as the beta. Only will be the case in the case of a bivariate regression. Other good questions that I can give confusing answers to, Ken?
I don't know if it's a good question, but back to the regression
Yeah.
question about salaries earlier.
Yeah.
Salaries typically do not go down, right? So, I mean, so you were using.
And you can't have negative publications either, right?
Yeah. Well, you could. Yeah.
There's no. You can't have public. You can't have. Its lower bound is 0, right?
Yeah. So, I guess what I was getting at is that what if you were using something other than salaries in publications, something more like sales, where it was governed by how many goods were up and down of selling a particular good or whatever, where there were negative values as you go, like this month up, next month down, and how does that get factored into the regression equation?
Well, the analysis would be exactly the same, in that what the regression is going to do for us is maximize sums of squares regression, the good regression, and minimize sums of squares residual. And in that case, it may or may not be able to do that in a way that will make a meaningful predictor, right? I don't quite follow your example, other than clearly the data that I have is made up and fabricated for our edification here. In the real world, it's not this pretty, and there's all kinds of scenarios that we are up against, but the same logic applies in terms of what the regression is able to do for us. And so, I mean, an example, and this probably we could do, and I haven't done this one specifically for my job, but it could be where we're interested in. We want to predict first semester GPA here with their high school GPA, let's say, right, or their ACT score, something like that, right? So I could get what's their overall GPA at OU first semester, and then I could get, well, what was their high school GPA, and we could have the analysis would do exactly the same thing. It would find the best intercept and the best slope such that our sums of squared regression is maximized. It might not be very meaningful because maybe there isn't much of a relationship there. I happen to think there is probably a moderate sized relationship between the two, but what it's doing intuitively or behind the scenes or what the analytic is, it's the same thing. It's looking at, it's trying to maximize sums of squared regression and picking the line that will do that in a way that it maximizes the sums of squared regression. And then when we start talking about multiple regression, we start talking about it's a multiple dimensional space that we're working in. And so it becomes a more complicated proposition. But that logic still applies where it's going to give you a sums of squared regression that you could change any of those b's, and if you change any of those b's even just a little bit up or down, you're going to get your sums of squared regression is going to go down. It's going to have maximized your sums of squared regression. So I'm not sure that was a.
Well,
I feel that
It's just all the
was like a
values
C
we're
plus
doing.
answer to an A plus question, but
it can only go up, because with your example, the values could only go up. I guess that just threw me off.
yeah. Good. Other questions? So we still have. God, I hate to throw away. What do we have? 10 minutes.
Yeah.
We'll throw away 10 minutes. So look at your homework number 2, which is at the end of the slide deck 5. Be thinking about the analysis you're going to do for homework number 2, okay? Which again you'll see at the end of not this deck, but the end of the deck that I put up there last week. And so for sure we should get through that slide set next week. So you'll have the homework number 2 due the week after, and you'll see with homework number 2, I have you do the analysis, but I have you calculate a bunch of things for me as well. And so, I mean, if you're just bored and you don't want to watch Netflix anymore, you could actually start doing some of homework number 2 now instead of waiting for next week. But that's maybe wishful thinking on my part. So I'll see you next week, if not before, and I'll have your homework graded and posted back to Canvas on Saturday.
The recording.
Let me restop the recording.